morning, everybody. We're Team Bits and Ohms, and our project for this semester is Autonomous Walking Robot. My name is Raylan Ramirez, and I'm the project manager.
My name is Michael. I'm the hardware lead.
I'm Brian, and I'm the report editor.
I'm Hector, and I'm the parts manager.
This semester, we're sponsored by San Diego State University, and our direct sponsor is Dr. Gordon. So why are walking robots important? As you can see in various fields, prosthetic legs are being made in the medical field and allowing individuals to walk and use the range of motion again. In the military field, we can see that autonomous walking robots are being built to deliver cargo to have our soldiers out of harm's way. So here's a quick presentation overview of what we're going to talk about today. So we're going to talk about the project description, our intended functions, how we integrated our parts, how we realized our design, which is broken up into four parts, which is the power supply unit, the system input, the control unit, and the system output. And then we'll talk about our algorithms and our flowcharts, and then we'll talk about some project management side, and we'll have a quick Q&A at the very end. Now I'm going to pass it on to Brian Murphy for our project description.
Thank you, Ryan. For our project, we were tasked with designing an autonomous walking robot to participate in SIE, Quantified Robot System Challenge. The SIE is the Society of Automotive Engineers. They're a global body of scientists, engineers, practitioners that advance self-propelled vehicles and systems knowledge for the benefit of mankind. The modified competition will consist of the robot traversing a randomly generated 3x5 grid. The 3x5 grid will have obstacles throughout that the robot has to be able to get around. And on the second run through, it'll be the same thing, but there will be a set of stairs somewhere in the middle where the red dot is in the diagram. And you can see some sound mazes for the first challenge. We can start at the bottom left corner, and we have to traverse through, get to the top right corner, so the robot will go right. You can see that middle is open, walk straight, and then walk to the right at the very end. Same challenge, same thing, except there's a set of stairs in the middle that has to traverse over. And moving on to the intended function of the robot must be able to fit into a 7-inch cube at its minimum size, meaning that if the robot expands beyond 7 inches during the actual competition, it is perfectly allowed. The robot itself also has to be completely autonomous, meaning there will be no tethers attached to the robot. Due to this restriction, the robot must also be powered by its own power supply. The robot has to be able to traverse a randomly generated 3x5 grid. We have to put emphasis on the word randomly, so no group tries to hard code in a specific maze. And finally, the robot must be able to tell the difference between an obstacle and a boundary. Obstacles in this case would be boxes or walls put in place throughout the obstacle course, and the boundary would be something like the stairs. It has to be able to know which one it can avoid and which one it will be able to find later. Now I'll be passing on to Michael to talk about the design realization and integration of the robot.
Thank you, Brian. After Brian explained the rules and the intended function that we want our robot to have, my team and I had to brainstorm and really visualize what type of components we need to achieve these goals and how we'll be integrating. So here's a little preview, a little glimpse of our robot. It kind of, if you're accustomed to Disney, it kind of looks like a ghetto Wall-E. So it's utilizing many components that we decided to fit. For example, we're using the Arduino Mega microcontroller. We're using voltage regulators so that it hits all the operating voltages for all our peripherals. We're using an ultrasonic sensor, which will be the eyes, which will basically gather data for us while we're traversing the maze. We're using a quadruped plastic chassis as well as actuators to provide movement and a basis for our entire robot system, and a single power supply to power our entire robot. We're also using a servo driver in order to preserve most of our EWMs. We're also using for our actuators and such. So this is a more top-level systematic diagram of that same picture of that robot. We broke it down to 4 main parts. So we have the system input, which utilizes our ultrasonic sensor. We have the control unit, which is kind of like the brains of the operation, which will use this data and then we'll create algorithms in order to traverse the maze. We have actuators, which provide the output, and overall, it will be controlled by a single power supply unit. I'm going to start us off by describing the power supply unit. So we use a LiPo 7.4 volt battery. The reason why we use it is because of its lightweight and its size. It's like perfect for our project. We did several tests, and then we also used a voltage regulator, a 6-volt voltage regulator, in order to power the servos properly so it doesn't get overvolted. And we used actually Arduino voltage regulator of 5 volts to power our sensors, because that was their operating voltage. We did a couple of tests, my team and I, to see how long the battery would last. So we tried to run the robot as if it was in full load. So full load meaning everything's working at once. So we're sensing the sensors are sensing, the actuators are moving constantly. And we found from our graph here that it lasted from around 14, 15 minutes more or less. So from here, from this calculation, from this graph, we actually calculated the current's maximum output to be around 4 amps. And as intended, the regulators work properly because all our devices work properly without any problems. I'm going to pass it off to Aitor to explain the system input.
Thank you, Michael. So the input for our system is provided by the ultrasonic sensors to the Arduino. These sensors send out a ping and receive an echo. The signal is a pulse where the width determines the elapsed time between that ping and that echo. We can later on translate that into distance by using the formula that you can see on the slide. I would like to talk about the control unit. The control unit for our system will be an Arduino. This board will receive the information from the different sensors, and according to that information, it will output one of the 5 different algorithms: walk straight, walk left or right, stand, go upstairs, and straight. Yeah. Now I would like to talk about the system output. The system output is provided by the Arduino to the servo motors. The signal is a pulse train, where the width of the pulse determines the desired angle for each motor. We have a total of 8 motors per day. I'm going to pass it to Jeff to talk about the different algorithms.
Thanks, April. So we have a couple of functions for our robot. We have a basic walk straight function, which involves the robot's diagonally opposite legs. So rise up, move forward, come down. The other ones do the same thing as well. We have a stand function, which is primarily used for providing a stable sensing platform for our ultrasonic sensors. Because initially we had a walk-in sense, but we noticed the robot's body bobbles up and down, so then it would like sometimes over the walls and it would crash into it and break surface. And we have a crab walk left and right, which just has the robot shimmying right, left, or whatever. And we pretty much just decided to go with that versus a turning function to remove the inconsistencies we had with turning. And one of our critical functions is our straighten function, which involves using 2 ultrasonic sensors on the right side to stay parallel with its wall on the right. So the way it works is, say the robot's oriented like this, it's going to notice its back right sensor is shorter than its front right, so it's going to just turn, or the other way. We also have a stairwalk function, which pretty much is a modified walk function, which just has the legs going up a little bit higher until they're both at a position where they're like on top of the second step. Then the back ones are moved for the robot to shimmy closer and enough for the back legs to go ahead and climb up to the steps. And we use a similar procedure to send it as well. So our flow chart. So our flow chart is really just starting off with a straighten function, and then we stand, we gather sensor data, and then from there we decide, can we go forward? If not, we go left or right, and then we go forward again until we hit the very end, which will just be if this is my front sensor block, this is my right sensor block, and we're done. And that's pretty much it for algorithms. Ray will cover up the rest of the project plan.
So here's our project plan and milestones that we had for ourselves this semester. So by February 23rd, we wanted to purchase all of our main components, which included the sensors, the actuators, and the chassis. And then we wanted to test each of those individual parts by March 1st. And then by March 15th, we wanted to integrate all those parts to create an autonomous walking robot. By April 15th, we wanted to complete the first challenge, which was traversing the 3x5 grid with no stairs in the middle. And then by April 30th, we wanted to traverse that same grid with some stairs in the middle. And then some milestones that we have for down the road is on Thursday, we're going to want to compete in the walking robot competition against the other teams. And then by the end of the week, we want to deliver our product for senior design day. So here's a quick picture of our cost analysis. This includes all the parts that we spent on. The most that we spent on was our chassis and the servos and the microcontroller. As you can see here, we spent a total of $231 and we have the remaining $69. We just want to give a quick special thanks to some people in the room. We'd like to thank Dr. Gordon Lee for helping us throughout the semester and just basically teaching us the basics of how to create an autonomous walking robot. We'd like to thank Mark Bruno for helping us in the lab with any supplies that we ever needed. I'd like to thank Dr. Tamala for opening up the section and allowing us to participate in senior design semester. I'd like to thank John Kennedy for teaching us some engineering fundamentals inside and outside of the business world. And I'd like to thank the rest of the electrical and computer engineering department, just basically teaching us the fundamentals throughout our 4 years here at our 10 years. So we'd like to end with a quick video of us finishing challenge 1, which we start on the bottom left grid and traverse through the maze. So as you can see here, we're starting off to detect the wall, so we're going to move to the left. So if we're ever off balance, as Jeff was explaining, we use our straightening function to align ourselves straight and continue to move forward. It's going to get good.
Promise.
So if it ever gets too close to the wall, to the right or to the left, it'll crowd walk away from it, as you can see. So now we're approaching the end of the maze, and we should know that this is the stopping point, and we should detect this. Our sensor should detect the walls and tell us to stop. And there you go. So with that being said, thank you for listening and opening those questions.